Hello, class. Welcome to this Lab 6 demonstration for MMCV 211. This week, we'll be looking at a plane stress analysis problem, wherein we have a plate undergoing a uniformly distributed load, tensile load, with a slot in the middle, and we have to try and find the maximum stress in the plate. So before we jump into the lab manual, I'll talk about what we'll be trying to analyze and how we'll be trying to analyze this. So we could initially model the whole plate with the entire slot. But the whole purpose of FEA is we're trying to get results as soon as possible or as quick as possible and most effectively. If you're able to visualize, this plate is nothing more than a plate that is symmetrical, right? It's symmetrical about its x-axis as well as its y-axis. Okay, so in this lab, we'll be using something called symmetry boundary conditions, wherein we will simulate or we will model just a quarter of this plate, and we'll apply a boundary condition here that is symmetrical, basically meaning that this member will be flipped and accounted for on the other side. And we'll also be modeling a boundary condition along the y, so that this member is also flipped across the y direction, just to simulate that it is equal and opposite on the other side. So that's what we'll be doing in this lab. The whole purpose of this is to reduce the number of nodes and generally to reduce the total processing time. Okay, so jumping right into the analysis today. First step, you should always set your preferences. So preferences, structural, okay. And your units. So /units, SI. You also have to save a file path. So we'll go to File, Save As. I'll name this Lab 6. I want to save it to my desktop. Save the file name. So we'll go change the file name, and we'll do this as in stress analysis. Essentially, what a plane stress analysis is a 2D analysis. So we won't be considering the thickness in this modeling scenario. Why? Because we're assuming that the stress will be constant throughout the thickness. And we're only interested in the stress distribution in the XY plane, not the Z plane. Title. So now we must define our element type. So we'll go to preprocessor. And for this, we will use a solid element. And we will select quad 4 node 182. Difference between quad 4 and quad 8. Quad 4 has less nodes. Therefore, it gives a slightly less definition to your answer. But for what we're trying to do, quad 4 should be just fine. You could also do it in quad 8, but when you go to the final extracting of results, bear in mind that you're using quad 8, and your keys when you enter for SMISC stresses will be different. Okay, so we created a new element. Just go to options and make sure that K3 is set to plane stress. We're only interested in the plane stress, not plane stress with thickness, just plane stress. Okay, once we've done that, we can close this dialog box. Now we have to set some material properties. So we'll go to material props, material models, structural, linear, elastic, isotropic. In the Young's modulus, we will enter 200 gigapascals and 0.3 for a Poisson's ratio. Once we've done that, we click OK, and we close the models. Once we've done that, we can start our modeling. Now, different from our previous labs that we've done, where we've used beams and we just draw lines, this time we're actually defining the geometry of the section using lines, and then using those lines to then help build an area. So we'll go to modeling, create key points, and in active coordinate system. Similarly, in the lab manual, you'll find the key points that we have to enter. We have 7 key points in total. So we have key point 1, coordinate 0, 2, click apply. Once you've reached the last one, then we can cancel or press OK before you press apply again. So now we have our 7 key points, and we have to create lines between these key points. Also, this is given in the lab manual. To create a line, we will go to create lines, lines again, and in active chord. And line number 1 goes from key point 1 to key point 2. Line number 2 goes from 2 to 3. Line number 3 goes from 3 to 4. Line number 4 goes from 4 to 5. And line number 6 goes from 1 to 6. Sorry, line number 5. Once we're done, we can click OK. Now we want to display the line numbers. So we'll go to control plots, numbering, turn on key point numbers, turn on line numbers, OK, plot, and then multi-plots. We can see all of our line numbers. Once we've done that, we want to try and create an arcing line from this point to this point. In order to do that, we will go to preprocessor, modeling again, create lines, and instead of lines, we will select arcs. And we will select by n key points and radius. Now we pick key point 5 and 6. We click OK. Then we select key point 7. We click OK. This dialog box will pop up, basically saying that we're joining an arc from 5 to 6 with the center at key point 7. We have to enter the radius of our arc, so we'll enter 0.02. and we'll click OK. So now we've clearly defined all the geometry of our quarter section that we're modeling. So now we want to try and create an area by lines. In order to do that, we go to main menu, preprocessor, modeling, create, and not lines. We'll go to areas, arbitrary, and by lines. Once we've done that, then we can pick all the lines. And what this does is it essentially just creates an area within the lines that you specify. Click OK. And now we've created an area within the lines that we've specified. Upon finishing this, we can now mesh the area. So we'll go to meshing, mesh tool. And in the size controls, we will go to areas, select set. Now we select the area and click OK. And in the element edge length, we will enter 0.002. We click OK. Now, still working in mesh tool, we will select mesh. This warning may pop up. The mesh of area 1 contains triangles, which will be too stiff in bending. So what this essentially means is whenever we're trying to model something in FEA or using finite element analysis, we want to stay away as much as possible from triangular elements. For the details of that, you can go online to search why, but I'll give you a brief explanation. Triangular elements don't display strains across the lengths, okay? So they don't give accurate stress or strain readings across the surface, unlike quad elements, which can display the stress across the X and Y direction. For triangles, they can't do that. So as much as possible, we try and stay away from triangular elements. Again, for the details and for your lab report, you may want to look into why triangular elements aren't ideal. But for now, we can just close this warning. Now we're going to start applying our loads. So we'll go to main menu. We'll go to loads, define loads, apply structural, and we will apply a pressure on lines. And we will select line 2. Now, if you've forgotten where line 2 is, just you can just hit multiplots. So line 2 is where we want to apply our pressure. So we'll select line 2, OK. And the pressure value that we'll enter is minus 50 E. The reason we click negative is because by default, the pressure direction would be into the line. When we put it as negative, it'll be going out from the line. Uniform pressure being applied to the line. Now comes the part where we apply our symmetry boundary conditions. In order to do that, we go to loads again, define loads. Loads. Apply structural. Structural displacements symmetry boundary conditions, and then we select on lines, and we have a boundary condition about line 1 and line 4. Once we select those lines, we click OK. These small s's signify that there is a symmetrical boundary condition about that line. So essentially, this member is being flipped about the x-axis here and flipped about the y-axis this way. Now we've done all the boundary conditions, we've done the meshing, we've done the modeling. So now we can go ahead and solve. So to solve, we just go to solution, solve, current loading system, and click OK. Solution is done. Close this status command. So these small triangles show the symmetrical boundary condition. The only load we applied is the load on line 2. So now we can go to General Post Processor. We go to Read Results, and we select Last Set. Then we can go to plot the results. So we will go plot results, contour plot, element solution. We'll look at the stresses because we want to find the maximum stresses, and we'll look at von Mises stress. You may also want to, for your report, briefly explain what von Mises stress is. It's essentially a combined loading stress. Then we'll click OK. And now this is our stress field with the contour plots. And you can see that our maximum stress occurs right here at the base of the slot. So in your report, you may comment on the location of the maximum stress and whether or not it's backed up by research or by theory. And our minimum stress occurs down here. So these are the main results that you can extract from this experiment. And for part 2, you are supposed to, instead of modeling this with a slot, so without this straight edge before you go into the curve, you just want to create a circle up in the top corner. And that'll be, then you make the comparison between a slot and a hole. Thank you very much for listening, and good luck with this experiment.